Hello, welcome to another video from the Inner Forces series. Today you will learn how to solve a truss using the method of joint equilibrium, as well as how to identify zero-force members in the truss. We have this truss, and we need to identify the zero-force members for this given truss, and determine the forces in all the joints using the method of joint equilibrium. We have a horizontal force of 10 kN applied here, 20 kN, and a vertical force of 15 kN. We have a hinged support that does not move, and a sliding hinged support. So we already know that in the fixed hinged support, there are two reactions. In the sliding hinged support, there is one, perpendicular to the direction of the slide. We have dimensions of 4 by 4 by 3 and 3 vertically. So let's get to calculating. As for the truss, we need to number all the members. So I marked them here in green, 1, 2, 3, 4, 5, 6, 7, 8, 9. We could also label all the joints, but I will solve this a bit differently. You will see how shortly. We could also label A, B here, and the rest C, D, E, and F, let's say. But maybe we will try to label the joints a bit differently later. The first thing we need to do in such a truss, just like for a regular beam or frame, is to calculate the support reactions. That is the equations of static equilibrium. So we start with the sum of moments at point A, as this will be the simplest for us. We will immediately calculate the reaction VB from this. Now, we need to clearly define here, to avoid making mistakes at this first stage, what the moment arm of our forces is. So the moment arm, I will repeat for the umpteenth time, is the perpendicular distance from the direction of action of the force to the point, that is, to the pole of the moment for which we are calculating the sum of moments. So we are working at point A, and we have that the reaction VB is its direction of action, that vertical one. The shortest distance, meaning the perpendicular, is here, which is 8 meters. It rotates clockwise, meaning for me it's positive. I assume when calculating reactions that clockwise moments are positive. Next we have that 10 in the equation. It rotates counterclockwise with respect to pole A. And this is its direction of action, that horizontal, while the moment arm is the shortest distance from this horizontal segment to point A, which is this distance here. This is 3 meters, so minus 10 times 3. Then this 15 here is the direction of action. Here is the arm. It acts counterclockwise, minus 15 times 4 and minus 20 counterclockwise on the arm. And now the direction is the same as the force 10, that is the direction, while the moment arm is the perpendicular distance from this direction of action to the pole of the moment, which is minus 20 times 3. This is one of the difficulties with trusses. I think it's not a big one, maybe more for beginners. And the second difficulty with trusses is that these forces here are often at an angle in these truss members. And a common mistake is the wrong distribution of these forces into the vertical and horizontal components. Those are probably the only two difficulties in trusses. So it turns out that VB is equal to 18.75 kilonewtons. Now, the sum of the projections on the y-axis, so we have VA going up, 15 going up, and VB going down. From this, we calculate the reaction VA, which is 3.75 kilonewtons. And from the sum of the projections on the x-axis, we calculate the reaction HA, which comes out to minus 30, meaning I assumed the direction wrongly, so I'll change it right away. So HA acts, maybe I'll use red color, not to the right, but to the left. And here we have a little plus, okay. And once we have calculated the reactions, we move on to the equilibrium of the nodes. Before I tell you how to find zero-force members, I will show you what the equilibrium of nodes is about. Then it will be easier for you to understand. So let's establish the equilibrium at node A, and I'll refer to them this way. Node 1. 3 is the node where bars 1 and 3 converge. I could call it node A, but then the next one will be this node, and I'll call it node 1, 2, 4. I mean, I don't know if this will be the next one, but that's what I'd call it, 1, 2, 4, where bars 1, 2, and 4 converge. Okay, equilibrium of node 1, 3. So this is what it looks like. We cut out this node, so we have this intersection and this intersection. And this intersection of the bar is infinitely close to this node. So we see the forces acting directly on it, namely reactions HA and VA, as well as forces in these bars. Sorry, the intersection is in the other direction, of course. The intersection is in the other direction. And from the intersection, forces are acting. I mean, they can be directed towards the intersection, but what was the convention for marking normal forces? If I mark them with the direction from the intersection outwards, I assume that the bar is being stretched. If I get a positive result, it means that it is a tensile force. If I get a negative result, I assumed the direction incorrectly, and in that case, the force is compressive, meaning the bar is being compressed. And for such a situation, for such a cut, we have at our disposal the sum of the projections on the x-axis and the sum of the projections on the y-axis. And you can immediately see that we will need to project this force N3 onto the x-axis and the y-axis. And now to do this efficiently, what do we need first of all? I have already marked the angle of inclination of the diagonal bar here. It is here. We need to determine the sine of this angle and the cosine of this angle. Well, I guess I don't need to tell anyone how to determine the sine and cosine of an angle. My sine and cosine went missing somewhere. Oh good, here they are. The sine is 3/5, which is 0.6 comma. The cosine is 4/5, which is 0.8. So now I will show you a principle that I find easy to apply, and I think it's a good simplification. Let's say this is our force N3. And I calculated the sine and cosine of this angle that I highlighted now. Then when I break it down into horizontal and vertical directions, the components are here and here. One could draw right triangles and continue writing trigonometric dependencies, but it will always be in the way I will show. If there is some force here, let's say P, then the component where there is an angle, that is the horizontal component, here is the angle, and here there is none. This is the component where there is no angle, as it were. So that component where there is an angle is always with the cosine of the angle that I highlighted. Let it be angle alpha, then this is P times cosine alpha. The component where there is no angle is P times sine alpha. So P times sine alpha, and I have already determined sine alpha and cosine alpha. Now look, if I were to calculate not this angle, but from the other side? Because I calculated this one, meaning this one, and if I were to calculate this angle, the sine of this angle and the cosine of this angle, well, then it would be here. And this one will be beta. Then this vertical component would be with the cosine of the angle, but beta, while the horizontal component would be with the sine of angle beta, because now angle beta is with the vertical component, so the vertical component is with the cosine of this angle, while the horizontal component would be P times sine beta. And since... God, how awkward this is, sorry. Since alpha plus beta equals 90, sine beta equals cosine alpha. That's why it works out the same here. But you may have more strange trusses where these angles will be different and more difficult. So as I said, that's the difficulty when it comes to trusses. Well, all right, we have sine, we have cosine, we already know how to break it down. So I break down N3 horizontally with cosine alpha and vertically with sine alpha. And we have the sum of projections on the y-axis and the sum of projections on the x-axis. So on the y-axis we will have 3.75 upwards, which is positive, minus N3 times sine alpha. If you want to start from the sum of projections on the x-axis, of course you can, but you will immediately have two unknowns, N1 and N3. And if you do the sum of projections on the y-axis, then this force of 30 and this N1 do not count towards this sum of projections. That means their projection on the y-axis is equal to 0. Because they only have a horizontal component, they do not have a vertical component. That's why it's better to start with the sum of projections on the y-axis here. All right, we know that, so now I calculate n3 from this. 3.75 divided by 0.6 gives us 6.25 kn. And for the sums of projections on the x-axis, we have minus 30 plus n1. No, and the component n3 in the horizontal direction, that is, plus n3 times cosine alpha, equals 0. From this, I have n1 calculated as 25 kn. So each time, we will cut the joint. Well, now think about how I would cut this joint, that is, the 1, 2, 4. And I wanted to do, well, here I have, of course, the reaction. Here I already have this reaction 1 calculated. I do not have the force N2 calculated. Well, there are only 2 horizontal forces. They have only horizontal components. The force that has only a vertical component is from the sum of the projections on the y-axis. For this cut, we see that this force N4 must equal 0. Because only this force N4 enters into the equation for the sum of projections on the y-axis. And this is precisely the method for finding 0 bars. We look at the joint. Well, after some time you will get used to it. And you will immediately know that this vertical bar must be a 0 bar, unless there was a force applied here. Then it would have to balance that force. But since there is no vertical force here, and this bar is not loaded with any vertical force, the reaction in the bar N4 must be equal to 0. Well, good, so we know that bar 4 is 0. I can mark 0 right away. Now let's look at the joint 6, 8, 9, that is, at this one. Similarly, from the sum of projections on the y-axis, joint 6 is 0. Well, someone might say, but wait, if I cut the joint 2, 5, 6, 7, that is, this one, so it might turn out that the reaction VB acts on this bar. Unfortunately, that's not the case. I mean, it simply isn't. If you look at joint 8, 6, 9, and it turns out that this bar is 0, then there is no other option than that the reaction VB is distributed only on bars 5 and 7, but not on 6. If from the equilibrium of one joint it turns out that this bar is 0, then it cannot be 0 on one side and non-zero on the other side. It is simply 0. Well, good. Let's take a look at the bar 7, 9. Sorry, at the joint 7, 9, where the bars 7 and 9 converge, that is, at this one. If you cut this joint, we would have the reactions N7 and N9. Whereby the reaction 9 and force 20 are only horizontal. So they only enter into the sum of projections on the x-axis, do not enter into the sum of projections on the y-axis. So if we were to do the sum of projections on the y-axis for this cut of the joint, N9 does not enter into this equation, 20 does not enter into this equation, only reaction N7 enters. No to N, 7 times some sine or cosine should be equal to 0, which means this rod is also 0, so N7 is also 0. And you see, from such a truss where we have 9 nodes, at first glance we can determine 3 0 rods. Okay, so let's move on. So we calculated the reactions N3 and N1. And now, as I said, I immediately assumed they are under tension. If I get a positive result, it means they are under tension. And now I am drawing a diagram on this truss, so the rod. On rod N1, I have a positive 25 kN, and the diagram on the truss is often drawn with arrows. If we get a positive result, the forces are directed towards the center of the rod, as I assumed in this section. N1 is directed outward from the section at the node, which is towards the center of the rod. It came out positive, which means it is as I assumed. And that is 25. If it had come out negative, the forces would be directed outward from the rod, meaning towards the node, contrary to what I assumed at the beginning when drawing the cut node. And N3 is also positive 6.25. This diagram will be ugly, but you will know what it's about. 6.25. Now I will move on to the next node. There is one more thing I haven't mentioned. We can only balance nodes where we have 2 unknowns. So we could start balancing either from this node, because here we had this unknown in rods 1 and 3. We couldn't start balancing, for example, from, I don't know, node B, because we have 1, 2, 3, 4 unknowns, as many as rods. And here, for example, regarding this node 869, there are 3 unknowns, indeed. But as I already told you, from the sum of projections on the y-axis, it must be 0. So we can balance a node where we have 2 unknowns. Or there's a situation like this, where there's a 0 rod. Now we will move on to balance the next node, node 3, 4, 5, 8. That is 3, 4, 5, 8, meaning to the balance of this node, because here it is already 0, and here it is already 6.25. We are left with unknowns, n5 and n8, so we can balance this node. And we remember that here a force of 10 and 15 is applied, so we have such a situation. 15 from below, 10 to the right, 6.25 as indicated by the arrow. It is positive, meaning directed outward from the section. Here it is 0, so I didn't draw it. We have reactions N5 and N8 assumed outward, so I assume they are under tension. And what comes out, we'll see. Now we will take the sum of projections on the y-axis. So in total, we do not see the reaction N8 and force 10 along the y-axis. So here we have 6.25 comma, and now this angle that I marked earlier. Alpha, it was here, so its sine was 3 to 5. So if alpha is here, it is also here, meaning here. And now the question is, what angles are here? We have alpha such that its sine is 3 to 5, so if we place it here, then the sine of this angle is 4 to 5, and if we place it here, then the sine of this angle is 3 to 5, meaning alpha is still here. So, good. And now we know that we are throwing 6.25 with sine. Because if we were using cosine, we would throw it horizontally, but we are throwing it here vertically along y, so with the sine of this angle that is here, plus n5 also with sine. Because the angle is here, at the horizontal, and plus 15 equals 0. From this, the reaction n5 is equal to minus 31.25 comma, we can draw it immediately. So minus, which means the arrows are outward from the rod. And here, without a sign, just the value 13.25. And from the sum of projections along the x-axis, we calculate that 10 to the right. Minus 6.25 times cosine alpha, the horizontal component. Minus 31.25 times cosine alpha. So this force N5, it came out negative. So the sign goes the other way. If you want, you can also mark here that it turned out that N5 acts in the opposite direction. Just it's a bit dangerous to mark that here, because then I would have to change it to positive. But since I've already marked it on the graph as negative, well, in any case, it acts not as I marked to the right and up, but to the left and down, so the horizontal component is negative. The horizontal component acts to the left and the vertical component downward. To this we add N8, which acts to the right, so positively. And it must equal 0, thus the force in the rod N8 is equal to 20 kN. And we mark it. Positive, meaning towards the inside of the rod. 20 kN. So good, now one more thing. If we were to do the equilibrium of this node, it would look like this. All right, we cut node 124, meaning this one, so we have 25 to the left. So this reaction here is 0 downward. And for now, I assume N2 is positive. So from the sum of projections along the x-axis, N2 is equal to 25. And that's it, there's no great philosophy here. And we have the same situation at the bottom. Only the 9th rod receives it from the 8th rod. So the arrows are in this way, as on the 8th rod. And their value is 20. Well, that's it. So it is 20. We have calculated the forces in the truss rods using the method of node balancing. If anything is unclear to you, I encourage you to ask questions under the video. Subscribe to our channel. That's all for today.